I admit, with a bit of embarrassment, that I rewrote this piece at least 4 times in the last few months. Not because it is particularly complicated, I just couldn't find a way to describe it efficaciously. The reason will be apparent in a moment. Eventually, I cut 80% of the initial script and decided to rely primarily on practical examples. The 1977 variable lag pursuit stern conversion intercept technique is based on the approximation of the intercept curve for a 5:4 speed ratio. This VIII equation is used to determine a series of parameters, but when you look at it, the standard DCS player's reaction is, "Sir, this is a game." But in a curious twist, this method eventually turned out to be simpler than expected, but only once I used the old IT guy's best friend. Flowcharts sketched on a piece of paper. Before seeing the wonderful flowchart I put together, we must introduce a couple of variables, some old, some new. Kata, indicated as theta sub c, is the familiar collision antenna train angle, ergo the relative bearing, ATA, when a collision course is established. R15 lag is a new parameter. It represents the range at which the target is moved from the collision course to 15 degrees on the cold side of the scope. For the maneuver, a 45-degree angle of bank turn is usually executed. DTG, or degrees to go, is another familiar concept from the discussion about intercept geometry. It represents how many degrees the fighter should turn to match the target's heading. For example, 135 DTG means that the fighter should turn 135 degrees to match the target's heading. 180 DTG means that the two aeroplanes fly in the opposite direction, ergo the fighter flies following the target's reciprocal. DTG is referred to in modern times as HCA, acronym for Heading Crossing Angle. DTG's supplementary angle is the cut, a concept used mostly in the US Navy and now considered obsolete. This technique uses DTG to monitor and adjust the lag angle as the intercept progresses. From the mathematical obscenity above, 3 constants are obtained, 600, 100 and 50. These values are intertwined with range and angles to determine 3 checkpoints. In premise, R15 lag, the value of this variable is determined as 600 divided by kata. Next, the lag angle to nail at 135 degrees, which is obtained as 100 divided by the range, but with some caveats we will discuss later. Lastly, the lag angle to be matched at 90 DTG. As you can imagine, it is calculated as 50 divided by the range, but again with some caveats. Since the technique described has a series of peculiarities that can confuse ab initio and veteran players alike, I put together a flow chart to better understand it. I found it to be particularly useful, and I hope you will share the same sentiment. Starting from the beginning of the flow, the crew should maneuver to place the bandit on a collision course or flying towards its reciprocal, ergo 180 degrees to go. I suggest setting up CC as it makes further calculations much quicker. This setup is typically and easily provided by a human GCI. Unfortunately, in-game AI controllers are not as useful. I described how to assess the necessary parameters in a dedicated video. Whist at it, there are additional parameters to assess which will be required later. The cold side of the scope is immediate if CC is being set up. If not, kata should be assessed as well. The bandit's heading instead is immediate if 180 degrees to go is flown, since it's the reciprocal value. Once those numbers are known, it is time to enter the thick of the intercept, starting with determining R15 lag. R15 lag can assume 3 values, less than, greater than, or equal to the range between fighter and bandit. Remember that the 2 aeroplanes are in motion and the range decreases quickly, so try to be on point with your calculations. If R15 lag is smaller than the range, the target should be placed on a collision course and held there until the range and R15 lag match. If you have followed my suggestion initially, you have basically nothing to do besides waiting. Then, follow the next subcase. If R15 lag equals range, then the target should be placed at 15 degrees cold and maintained there. Keep in mind that since no CC is established, the fighter will have to increase its angle of bank to maintain the lag angle. Lastly, if R15 lag is greater than the range, the fighter needs room to maneuver, and the target should be placed at 45 degrees cold and held there whilst the next oddity is computed. The idea is to anticipate the lag angle at 135 degrees to go. To do that, we check the range at 180 degrees to go. During the turn, in fact, the target likely has passed through the 180 degrees to go.
Save! Degree to go. again. I dare you. I double dare you, mother.
Degree to go.
One more goddamn time.
That's when the range is evaluated and ad hoc action is performed to further hold 45 degrees cold, or place the target to 15 degrees cold. The effect is to have the stick monkey janking the stick all over the place, but this is expected. However, as we will see in the third practical example, if the flow becomes too overwhelming, which is likely when flying without a human pilot or wizzo, holding 45 degrees cold until 135 degrees to go still works, with the caveat that 90 degrees to go will come up quicker than expected, and the overall trajectory will be larger and rounder. As the intercept enters the final phase, the cases described before converge. The crew should be proactive and calculate the lag angles at 135 degrees to go and then 90 degrees to go. The last step is making sure that the fighter is in the correct position and not too fast or too slow. If the flow is followed correctly, the manoeuvre should have the fighter rolling out 2 nautical miles behind the target for a speed ratio of 1.12 to 1 or 5 to 4. The classic 500 knots versus 400 knots, in other words. A series of examples is now presented. The third is the most interesting and complete, but also the one with the highest pace. I recommend checking the previous two before venturing there. The following is my very first successful test applying this technique. There are a couple of errors I will highlight later on. The reasons why the previous attempts did not work are actually interesting. For example, I lost the target in the side lobes. In this video, I was more proactive and tried to adjust the gain in advance. Another reason is keeping track of everything whilst doing maths and remembering the steps to follow. That's why I made a dedicated kneeboard page. In the scenario running, a collision course is already established and the target's heading is 300. Any human GCI can help with that, but DCS is DCS. Since CC is already established, R15 lag is easy to assess as soon as the target appears on the radar. In this case, kata is 20R. R15 lag is therefore 30. Following the flowchart, since R15 lag is greater than the range, we hold CC until the range matches R15 lag, and then we turn to place the target at 15 degrees cold. Once there, the tricky part starts, guessing the range at which 135 DTG is achieved. Then, apply the appropriate lag angle. DTG is easy to assess. This is nothing new, and we can use the BDHI to monitor it. Since we want to hold the target at 15 degrees cold, the pilot has to input a slight turn, which in turn changes the DTG angle. Once 30, short for 300 degrees, on the BDHI hits the mark near the label man is located, we have 135 degrees to go. That's when we apply the lag angle. Eyeballing the range and the lag angle takes a bit of experience, but with the kneeboard pages I made, the mental maths component is reduced to a minimum. In this case, it seems that 135 DTG is reached at circa 13 nautical miles, leading to an 8-degree lag angle. A slight correction is therefore necessary. As you can see, my angles are not precise. Lack of experience on the new method, having to monitor the radar, the BDHI speed and altitude, and finding the kneeboard data all require some practice. And of course, there is a reason why I don't play as a pilot. This is even more true as the Phantom II approaches 90 degrees to go. The range goes down fast, but the lag angle at circa 6 nautical miles is still close to 8 degrees and, in theory, no correction is necessary. This method is conceived to result in a 2 nautical miles rollout behind the target, so as we approach such a range, V sub C should be controlled, and the target placed where necessary. In case of a tanker, for example, we do not want to end up at its 6, but on the dedicated area on its side. As we have seen, this technique is not that complicated once a bit of visual help is provided. I found it useful to have a flowchart to remind me of the flow and the tables with pre-calculated R15 lag and the lag angles for 135 and 90 degrees to go. If you have noticed, I never looked outside the cockpit, which is not something you should do, but I did it purposely to show how this method works in bad weather, low visibility, or at night. The most apparent issue is my inability to maintain the correct lag angle, but it is something that can be offset with some practice. Even so, the method appears to be working quite well. The problem with this method, when applied to DCS, is the lack of help from the GCI. I covered techniques to determine cater and target heading in another video, but they are both based on drift and therefore take time. Moreover, the variable lag pursuit intercept is still based on a 5:4 curve. Different speed ratios may affect the precision of the lag angle tables. This example shows how the radar can be used to speed up the process of determining CC and target heading via the radar display readouts and the DOT of the ASE, acronym for Allowable Steering Circle. Obviously, this means that a brief radar lock is required, something that creates a number of issues in DCS given how it is stubbornly fixated on the stealth factor. In this case, I'm aware of a contact somewhere in my front quarter at a fairly long range, but no information is provided beforehand. Usually, it is hard to spot such a target, and even the AI GCI can help by providing a BRAA, which is then translated by the crew in ATA. Once the Wizzo knows where to look, spotting is easy. In this case, instead, I had to monitor the radar block by block until I noticed a smear not disappearing. Since the methods to evaluate kata and target heading are already covered in another video, to show something different, let's use a brief lock-on. Note that this is often suggested by the documentation. By centering the DOT and setting the aspect switch to tail, the crew immediately obtain kata and the target's heading, at least in theory. The DOT, in fact, has the tendency to jump everywhere at long range. Personally, I prefer the drift. In fact, if you have noticed, I used the drift to adjust the Phantom's course slightly and get close to a collision course. The intercept then continues as usual. Since the range is greater than ARM 15 lag, the collision course is maintained until the two values match at 20 nautical miles. At this point, the target is moved to 15 degrees cold. Per se is not complex, but I must highlight again how I lacked precision, as working on controls spread over two cockpits is not immediate. Previous examples showed the Phantom intercepting a Tupolev Tu-22, NATO name Blinder. Its size made it easy to spot early on the radar. What if, instead, we find a target at a shorter range? In this scenario, no information is provided directly, but a ground radar is present. Alternatively, the crew can use their radar warning receiver to narrow the search area. In this particular case, I spotted the target via the RWR-provided ATA before the GCI provided a BRAA. The minor drift towards the left revealed the right to be the cold side of the scope. The low drift ratio also indicated that Cater was not far off. I estimated 3 to 4 degrees, giving a correction of less than 10 degrees. Next, the heading. A Cater of around 10 degrees to 12 degrees means that the target's heading is approximated as 12 times 2.1, resulting in circa 23 degrees to 25 degrees. The Phantom's heading is circa 335, leading to an assessed target heading of 360 minus change. To spare my neurons, since I had a lot to monitor already, I rounded to 360. Now, all this computation required only a few seconds, which is not much, but at a V-sub-C of 800 knots, every second matters. Moreover, these are approximations. A lesson I am struggling to learn is to avoid fixating on the single degree, but be ready to adjust as needed. At circa 12.5 degrees, R15 lag is 48. The range is quickly approaching 25 nautical miles. The solution is turn hard to place the contact 45 degrees cold and hold until 135 degrees to go. Crossing 180 degrees to go, the lag angle to apply at 135 degrees to go should have been 15 degrees cold. However, I found that, thanks to my tables, I can actually find a more precise lag angle, in real time, so to speak, and I just have to monitor the range. Unfortunately, I was long on the turn to 45 cold, as I had the feeling the autopilot disconnected, which it didn't. Monitoring the closure, I expected the lag angle to be 10 degrees at 135 degrees to go. The lag angle turned out to be circa 9 degrees, but seriously, this is such a negligible margin. During the turn, I was close to 90 degrees to go, and I assumed it to be 8 nautical miles, corresponding to a lag angle of 6 degrees. Therefore, I kept pulling hard. It's a bit of a shame that I ended up wide earlier whilst manipulating the radar and the autopilots, otherwise the turn would have much more precise. Something I did not do, and on purpose, is verify V-sub-C. As Tacview showed, rather than being a 5 to 4 speed ratio, ergo a 1.25 to 1, this intercept was actually a quite absurd 1.65 to 1.1. If the goal is to saddle or at least avoid overshooting, the throttle should be managed more carefully. It is worth mentioning that the actual procedure involves even more dramatic maneuvers than what I showed. In particular, once the 180 DTG computation is satisfied, action should be taken immediately to hold the target at 45 degrees cold, or to hard turn in the opposite direction to have it at 15 degrees. Since I was flying on my own, that was a bit too much to manage at such a high V-sub-C, so I opted for the easier solution, which is holding 45 degrees. The drawback is that a harder counter-turn is required, and 90 degrees to go comes up very quickly. To wrap this technique up, here are a couple of final notes and considerations. As demonstrated, this technique is quite straightforward once understood. It is also easy to adjust to different requirements, for instance, different rollout distances. The discussion so far had in fact the objective of performing a 2 nautical miles rollout behind the target. If shorter or wider distances are required instead, all the crew has to do is to manipulate the constants. For example, if the goal is 1 nautical mile rollout, then the constants should be halved. Vice versa, for a 4 nautical miles rollout, they should be doubled. To keep things easy, I set up every scenario to be co-altitude. In reality, you may want to have a negative offset. Do not be afraid to reduce altitude. It makes the target more visible and yours harder to spot, assuming they are flying a properly made module. Obviously, the drawback is the necessity of updating the antenna elevation angle as necessary. In case no information is provided and you cannot or do not want to rely on your guts and experience to eyeball data, you can put the target on the nose. The zero antenna train angle situation simplifies several calculations and can be beneficial to AB initio players, especially. Thanks for watching, and take care.